Yes, now we can start.
Okay, well, thank you. Thank you for inviting. You know my name, Stephan Schulz. I'm working at the Baden-Württemberg Cooperative State University, or in German, EuroProofNet, and I'm developing EuroProofNet E. In case you know, it's complete coincidence that the university and its administration is on the side of the sobering monster, and EuroProofNet is on the side of the Greek philosopher in hoplite armor. I'm also a founding member of our Center for AI. So some people think I'm against AI. That's completely wrong. I'm a big fan of AI. Just have a differentiated opinion on LLMs, and I'm trying to transport this today. Talking about the future of the AI mass ecosystem, and I've divided the talk a couple of times. So currently it's LLM plus versus logic plus. Before we go to the future, we have to go to the present. And this is the mass ecosystem, approximately, let's be generous, now plus or minus 20 years. We have something called literature, and literature is written down in various ways, like you have stone plates with scribbled formulas, you have papyri with platinum slaves, you have printed books, but basically it's all fixed in a tangible medium. And it's all, nearly all, natural language with formulas. And then there's people who have been working away with literature and creating new mathematics by putting out more black ink on white paper. Some very few, relatively speaking, people have started formalizing mathematics. So they are converting math into logical languages and using formal tools, interactive theorem provers, partially automatic theorem provers, combinations of both, to build formalized mathematics. And of course, they want this to succeed. I have a couple of examples. Because the innovations behind what they're doing. MISA started basically as an attempt to formalize all of mathematics, starting at the textbook level and then going up. FlySpec was the attempt to formalize one particular proof by Tom Hales that was so complicated that reviewers said, yeah, we are nearly certain the proof is correct, but we can't guarantee it. And Tom wanted to have that guarantee officially on the record. We started a project that, of course, the project took much longer, but now it's complete to fully formalize the proof of Kepler's conjecture, which is that you can stack cannonballs the way you stack cannonballs. That's the best way to stack cannonballs. And these are where archive proofs. These are where people were interested in the theorem proving aspect. And then they noticed we have to use it for something, verification, but we need math for that. And so they started little different individual projects, and somebody said, let's have a big repository where we can combine all this and maybe create something useful for other people. So that's how Isabel formal proofs came along. And there's more such projects at the moment growing and becoming more and more useful. Okay, of course, now we leave the area of the land of light and beauty, mathematics, and come to what I call the age of artificial intelligence. So we have our pretty little math ecosystem as of soccer now. And now somebody gets down the LLM monster there, and the idea is it'll just keep on reading all those texts from papers, stones, and digital files, and consume everything and take over the field. But I don't only hope that's not the case. I'm fairly convinced that this is not the future of mathematics, but that you will have other solutions. And here's the reason. I like large language models. I mean, what they can do is amazing. They're really, really, really good at processing language. Now, we've all heard probably mathematics is language of science. I tried to dig out that quote, and apparently it goes back to Galileo Galilei, who said mathematics is language God used to write the universe, which is quite different, but then Galileo is pre-modern science. But that's just a quote, and I don't agree, and I think we all agree not to agree. Mathematics is not a language. There's a claim that mathematics is a language is the same misunderstanding as the claim that knowing how to develop software is knowing how to run a program language. Of course, we need to understand a program language, and we need to understand the mathematical language to be able to do mathematics. But that's not the heart of mathematics. The heart of mathematics is the definition, exploration of new structures and their properties, either inspired by intuitive notions or both today, often with very unintuitive notions. And you just state some axioms, they're interesting, and then you see what structures they describe, what are the properties that emerge. This is maybe useful or not. It's not about language, it's about structure and relations. Now, how do LLMs work? This is basically how all the current big LLMs are created. You take all the strings you can find in the world, usually by stealing them from the internet. Then you build a cluster that contains all or nearly all of the world's GPUs, put the strings in, and you get out a giant heap of numbers that represents a conditional, a model of the conditional probability of how strings will be continued when you have a certain context. So LLMs learn probability distributions. That is the important thing on language. We have a string, we have a context, and the question is, what is the next token in the string? Some people have called this stochastic parrots. Some people have likened it to the word prediction you use when you type something on your phone keyboard. And of course, it's much more advanced than that, but the idea here is exactly that they do learn properties of strings, tokens, not abstract theory, not abstract reasoning, and not even calculation. Except when they've seen one, they can probably reduce it. If you see 1 + 1 often enough, you know it's 2. But it doesn't mean you can calculate it in your head or in your model. And that also means that LLMs are basically reproductive. They can maybe remix things, but they don't create completely new things. They are not inherently creative. And that means they can do new mathematics. They can, of course, reproduce proofs they have seen, and because they have stolen all the words strings, they have seen very many proofs. They can reproduce a lot of known schoolbook mathematics. But my experience is they can't do reasoning from scratch. I have a couple of arguments for that. I mean, if you've been here last week, you've heard Jeff talking about Aunt Agatha. This is another paper where he's also talking about Aunt Agatha. Aunt Agatha lives in Redbury Mansion with her butler and with Charles, and she has been killed by one of them. The question is who? And if you ask an LLM who killed Aunt Agatha and give it the context, but back in 2023, that was Bart, when Jeff did the experiments, Bart correctly said Aunt Agatha committed suicide. He killed himself. But the reasoning chain it gave was wrong. Those intermediate steps were unsound. And the suspicion is, of course, it has seen this puzzle before. Because another thing that happened, when you systematically remove Aunt Agatha and Charles and the butler as split, split, and split, the split, slot, split, and split, and rename live in red dimension by diagonally in the plane, and replace murder by bamboozled and so on, then the model is completely lost. It can't figure out even this very simple argument. I'm not looking for papers of LLMs systematically. Everything I cite here are things that came up in my social media or in conference event, more or less at random. Very recently there was a big paper where they tried to figure out how well reasoning models actually can reason compared to normal models, giving them increasingly harder tasks. And they found out that especially the reasoning models, while they can handle short chains of reasoning, there's a certain point where they completely break down. Very hard, very how do you say it, ungraceful failure to reason this. And I was particularly interested in this other paper that is very new, where they used MLCP to generate a lot of logical consequences, and then filter of interestingness and for proof size, and then ask an LLM to reproof them. And they again noticed this works very fine for small examples, but as soon as the proof has more than 4 steps in for startup they break down nearly completely. Yeah, the other problem is they are unreliable. Not only can they reason, they can start to invent things if they learn a probability model and it's incomplete because there's incomplete data. The model has to give an answer everywhere, and so it may lead them astray and makes them put out what's normally called convincing but false information. That's fairly fundamental, the structure of LLMs. And it's not very easy to get rid of that. People have tried various ways. This very paper, the first one, claims that maybe you can get by if you punish models for wrong answers and encourage them to say, I don't know. But that's not part of the current structure. Currently, they just look for the next token and spit one of the top tokens out probabilistically. And there's a slightly older paper that I find interesting because it takes a theoretical computer science argument, and they claim they have proven that you can't avoid hallucinations in these models. Yeah, it's impossible that they necessarily have to hallucinate about some things, and so there's no perfect solution to that. I think, again, going back to that, my experience is I discussed this ChatGPT 3.5, which has been a while back, and I convinced it that 17 is a prime number. My argument was, well, you can divide it by 34, gives you 1/2, so it's divisible. ChatGPT said, no, that's wrong, because 34 is not an integer number. So I said, no, 34 is an integer number. And he said, no, you're right, 17, therefore cannot be a prime number. And that's something that you also see in this paper here. The models can reproduce definitions, but very often they fail to have a deeper understanding, but understanding the wrong word. They don't have a deeper abstraction behind the definitions, so they can apply them reliably. And that goes in various ways. Very famously, if you just give them words that shift the context, they very easily get lost. And it's not that they can be completely unrelated sentences, not connected to your question at all. Just by putting them in proximity, textual proximity, the models pick up on them, make them part of their probabilistic argument, and come out with very wrong answers. This last one is also something that came to me like a week or 2 ago, where they found out that one thing we know is that LLMs are very good at passing medical exams, multiple choice tests. And what they did is, okay, let's see how deep this understanding goes. So in all these tests, they took out the correct answer and put in none of the others instead. And performance of the models broke down, depending on which one you looked at, either nearly completely or at least by 25% or so. Again, it shows that there's not really reasoning behind that, but it's only statistics. And statistics are great for many things, but they are not good for formal proofs and formal mathematics. So if we look at this LLM, kind of unreliable. Oh yes, with its mountain of data, people have noticed that they can't compute. And so what do? They try to augment it, for example, by allowing it to run a Python interpreter. They can write a small program that can compute any numbers. Then they can suddenly compute, but it's not the LLM that's computing. It's just the LLM that has the control over a module that can compute. And of course, you can imagine adding a reasoning engine like a EuroProofNet, or a mathematical engine like Mathematica, or various other tools to augment them. That's what I call the LLM plus model. And the LLM plus model at the moment is very attractive from a business point of view, because LLMs are very popular, very impressive. They give managers and finance people the illusion that they can talk to a real AI. They attract enormous amounts of funding. And so by making your LLM seemingly better by adding external tools, yeah, it's easy to finance and the results are easy to verify, but it doesn't change the fact that the core of the system, the actual knowledge base, still is a giant heap of numbers that just describes a probabilistic model. You don't have a way to present really logical statements which have proper semantics and proper truth values. It's all just approximate. So, of course, if I say LLM plus is not the answer, what is? Good thing is ChatGPT is not all there is in AI. Large language models are just one application, deep learning. Deep learning is just one application, one version of neural networks. Neural networks are just one particular subfield of machine learning. And machine learning is one of the big subfields of AI. And of course, it's not the most important one. It's not an induction. Or maybe let's put them side by side, but let's put the logic and front. So my argument is we need logic-based systems. If we look back at history, mathematics has become more and more formal over time. My knowledge of history of mathematics is quite limited. My understanding is that Euclid was the first one who started to actually give formal definitions of things and build arguments just using the definitions. Then, about 1200 years later, we got Algorithmi, who formalized algebra and gave us the notion of writing formulas with variables. Another 300 years later, we got people like Newton and Leibniz, who extended this to notations that allow us to talk about infinitesimals. And we even had the attempt by Wilkins and again Leibniz to develop mathematical languages, a philosophical language that would allow us to formalize arguments in this language and then compute answers. So Leibniz famously said, let us not argue, let us calculate. Or that we all know that there was an e-project inspired by that a couple of years back. And then we started getting to useful languages like Schulz, Church, invented formal logics, and the rule is missing an E there. I programmed too much C and the logic text. And we had the first big attempt by Russell and Whitehead basically formalize mathematics, which hit a big snag when Gödel showed that we can't have a perfect system for that. We have the incompleteness of any system that allows us to describe natural numbers. But it doesn't stop people of continuing this line at the advent of modern computers. It has become much more doable, and also much more attractive, because now we don't have to do this formal reasoning in our minds or paper with lots of pen. We can ask a computer support us in doing formal arguments, and this increased productivity billionfold. And so my argument is we will not step back to a less formal natural language formal system that we have in LLMs. I think at least in mathematics we will stick with more formal logics, and we will build our mathematical systems on formal logics. I'm not alone in that. This is Edgar Dijkstra. Scientists will know him because he's one of the guys who invented formal verification, a very painful technique we have to learn in the first 2 years or so, and then usually don't use at all. And he had an opinion on using natural language to interact with computers. And my argument is computer science. The interesting part of computer science is basically applied mathematics. So the argument carries over to mathematics. He says, if our computers only understand natural language, the first thing we would try to do is to teach them to be precise and to do exactly what we tell them, and to unambiguously reply to certain stimuli. And that would be the hard part for computer science. I like this quote, and I think this is quite true. It's, one of the attractive features of computers that they are normally deterministic and do exactly as they are told. And it's one of the attractive features of mathematics that we have statements that we can prove not only beyond reasonable doubt, but beyond any doubt, modulo very slight human error. But then we have enough humans to check them over and over again. And I'm quite convinced that the statement 13 is a prime number is a true statement in the absolute sense. Okay. So I think at the heart of a future mathematical system, we'll have a big mathematical database that will be expressed in some form of symbolic logic, probably some version of higher order logic, but for efficiency reasons and for reasons of understanding, it will use a lot of first order sublogics. We also have other sublogics. Positional logic is always interesting. Yeah, my dream is, and I'm well aware that dreams don't always come true, that we will eventually manage to put all these data we have into one unified database with one unified format that allows us to use proofs done in lean. If you want to do something Isabel, or use C prover like E to prove something that has been stated in HOL4 logic. But I admit that's a dream, and mathematicians are like cats, very hard to one point into one direction. So maybe that's not true. But even if there are multiple such databases, each of them should be globally consistent. Each of them will have one format that you can export to and export from. Out of necessity, it will be structured. You will be able to put in new parts, indexing, be able to search it. And over time, it will become increasingly comprehensive. I think in 100 years, very little new math will be done on blackboards. Most of it will be done with the help of computers. scary thought is maybe all of it is done only by computers. I don't know. I hope we don't get there, because I think humans should remain in control and understand what's going on. But who knows? Okay. So then we come to the logic plus architecture. Let's move the system to the side and see what we can do with that. One thing we can do is mathematics formalizing the existing literature and converting it into formal logic. Of course, if you do that, you want to be able to check that actually what you do is correct. And one important criteria is check internal consistency. Our theorem provers, at least the current generation, are very great at finding inconsistencies because they're all based on showing the unsatisfiability of sets of formulas. So we can use them, and there's even some tools that allow us to not guarantee consistency, but to eliminate very, 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 very many inconsistencies. Guaranteeing consistency, unfortunately, for higher order logic doesn't work, and first order logic requires unlimited time, which we usually don't have, but we can get very close to this. We've done experiments with Psych, with Misa, and with Sumo. And we found some errors in Psych, found a lot of errors in Sumo. We found not a single error in Misa. Maybe that our tool doesn't work for Misa, but no, we had Joseph Urban put in errors on purpose, and we found those. But as far as we can tell, Misa is consistent. Sumo and Psych had errors that were fixable. And we could point out exactly which formulas clash. In Sumo, it was often that predicates were used that were related but not quite the same. I don't remember what the backing type was. Okay, second thing, if you want to add newly developed piece of mathematics into the big database, you need to check that it's consistent with the data we already have. And of course, inconsistency can only come if you have shared symbols, but then there's a risk that we have symbols with different definitions, or not quite equivalent definitions in one or the other, and that can lead to conflict. So we want to be able, whenever we import something, that we again check its consistency. Now, formalization is something some people like. I don't. My students hate it. I have to do that in every logic exam. And last year, for the first, we are doing first order logic. And I tell them 10 times over 10 lectures, if you nest a predicate inside another predicate that is so wrong I can't grade it, you get 0 marks. For the first time last year as it worked, and I only had 3 or 4, normally about half the students think that red of grade of x means that x is both red and grade. So people hate this, but here's something where the monster can be useful. There's a new field, when formalization, 10 years maybe, but it has really taken off with LLMs. LLMs are great at translating between human languages. And the idea is, why can't they translate from human language into mathematics? And they can, lots of errors, which again means you need to check it for consistency. But they do help, and I think in the long term they will become quite good and help us to improve productivity there. And then get more mathematics into our formal database. Okay. Now this is how we fill the database. And that is value itself, because it allows us to verify that existing mathematics is sound. It will help us root out errors, unstated assumptions, incomplete proofs, even if the results are right. Maybe there's some things that some cases have overlooked that can be fixed. And if you have a formal proof, we know everything works out perfectly. But what do we do if we have this database? So what's the output? One thing we can do is what we call iterative theory exploration. that's basically what people with about creating obligations for LLMs did. Our C improvers, many of them are saturating, which means they take facts, they combine them, and reduce logical consequences. Normally, the aim is put into the gate conjecture, you want to derive an explicit contradiction. The empty clause is a witness for inconsistency, and hence you prove a contradiction. Use the conjecture. But if you write not conjecture, they will happily just create consequences. So you can create more and more and more formulas. Many of them are boring, but some of them are interesting. And you can use tools to filter out interesting ones and allow you to create new math basically automatically. I've done something like this with Bruno Hochberger back in 2003. And for further logic, it worked quite well. For unification logic, it worked quite well. For further logic, back then, you could find very good, interesting criteria. There's better ones now, but back then we got a lot of boring crap. And the other thing is, if you just enumerate, you won't get that deep into interesting space necessarily. So there's another new approach where you use various methods to come up with conjectures which don't have to be true. And then you try to use them. Moore and Johansson is doing that in Chalmers, for example, and they use both LLMs and pattern-based approaches. Last time I checked, the LLM suggests for every binary function symbol, this could be commutative, this could be associative, this could be cancelable. But there may be other things. Certainly you can get other conjectures, and you can fully enumerating logical consequences of your input. Well, then that's the reason why we do all this, I think. We want to new theories. This is small lower corner, but really it should be the big screen. We want to provide tools that help mathematicians to come up with new sound theorems and create formal proofs immediately when they have the idea of what they want to prove. Currently, most of this is done with the accuracy improvers, although there's quite a lot of, there's some algorithms who use Otter, Prover 9, or even to work on algebraic theories. There recently was a big project by Terence Tao of classifying some sort of groups in some way, and they used, for example, autonomous improvers. Vampire alone could prove or disprove, I think, 2/3 of the database, although only after the fact. So that's one way, but most people use the accuracy improvers like Isabel or Lee, mathematics, but these use hammers. They use automatic improvers backend to help solve very simple subproblems and make things the mathematicians normally say, I say, oh, it's obvious, explicit. And this is one area where we use other AI techniques as well. We've been doing this for a long time, trying to ADPs, how to select the next step well to prove a certain thing. I think Sane here. Yeah. When last time I had this slide on, I said, and I also think translating formal proofs back to Q and readable proofs is a great application for LLMs. And I think you said, no, you want something more reliable than LLMs. But still, I think they can elaborate, convert it to more accessible language, let's say, like this, that maybe still needs to be checked. That's one use where I see LLMs in future as well. Okay, I want to talk just shortly, briefly about proof search guidance, because that's a topic that I am interested in. I started working on back in 1992, and all of my work has been in preparation for that. I've got a master's thesis out of that, I've got a PhD thesis out of that, but most of the time I've just built foundations, and then other people, especially Josef's group in Prague, have taken off and used that. ATPs normally use infinite search spaces. If you search for something in infinite space, you better look where you go, because if you're not careful, you may go for a long way in a direction where you won't find anything interesting. We found a couple of useful techniques there. One is look at existing proofs, check which search decisions have been useful, have contributed to finding the proof, which ones haven't. One thing I've been interested in for over 10 years now is if we have heuristics, can we express them in a language that's amenable to genetic optimization? And if so, can we optimize them? And the answer is yes and yes. I would have liked to say, and I have a new system now from a student that gave me fantastic results. And until 2 days ago, I thought I had. But what I found out is that there was a bug in the prover that some higher order configuration bled through to the first order case, which it shouldn't do. And if you select the wrong option there, this becomes incomplete, but doesn't know it. So it says satisfiable, 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 satisfiable. And the student counted all these as successes. So it turns out that the life is not as great as it should be, but we had a first generation of these tools back 10 years ago, and they already work really well on a small subset of the language we use to describe heuristics. And I'm optimistic that with the bug sticks, you will still get interesting, not quite so interesting results with the new system. Other techniques. We often have lots of different strategies that we can use to try to find a proof. And one thing we've tried to do for a long time, and again with mixed success, is look at a problem, figure out which strategy or which set of strategies is most likely to find a proof there. Last thing I have here explicitly is axiom selection. When I was young, which was like 40 years ago, 35 years ago, when we looked at theorem-proving problems, these had been designed by theorem-proving people and mathematicians, and they encoded exactly the knowledge that was needed in the axioms to prove the conjecture. Typically, you needed all the axioms. You dropped out axioms to your proof obligation failed to be provable. And that led to a certain style of theorem-proving quite successfully. But then a couple of years later, we started using theorem provers seriously for common sense reasoning with psych and sumo, and also simplification, where you translate basically all of your program into a giant background base of facts, and then you want to prove a property of one little loop. And nearly all of the axioms you have generated from your code you don't need. And common sense reasoning, if you want to prove a property of, I don't know, birds, you probably don't need to consider yourself with properties of how fast cement concrete sets under certain conditions. So you want to select the axioms that are likely to be useful for your proof. And again, that's something that is very amenable to learning. Spark has great successes there. Just looking at a giant axioms like conjecture, figure out which axioms may be useful for proving this conjecture. Yeah, when I started this in 1992, I thought this can't be so hard. We're gonna nail this in 5 years. We have made reasonably great progress, great successes, but it's been a lot harder than I thought. One reason is that up until about 10 years ago, our main problem was memory, both hard disk memory and random access memory. Our provers are so fast, they fill up all you can think of with lots of garbage. And back when I started this, I could store one proof on the hard drive at a time. One. Because the proof size was about 20 megabytes. My hard drive booter was 30 megabytes. Nowadays, 30 megabytes is one picture from an iPhone or so. So now we can work with great data amounts in make much more progress. Okay, one thing I left out, of course, is all these deductive techniques, theory exploration, and mathematicians through the series, of course, produces new results that need to go back into the database, or can go back into the database and help us grow it further. And again, I think in 100 years, this will be the predominant mode in which we do mathematics. We'll have systems that help us develop theories, and of course, they will store everything, make it accessible for others to use. Okay. So I think the future belongs to hybrid systems, but we need to have the logic in the center and other AI techniques supporting the logic system, not have an LLM in the center and have other tools supporting the LLM. Because our field allows for exact formal definitions without any ambiguity. And it's a great strength shared by the science and by math. We're talking about things we create. So we are in control. We are in control, and we can do it in an unambiguous way. Yeah, mostly talk about what we want to do. So if you look at this again, my vision of the future is we have this unified database for mathematics. We have people and robots and computers working and filling it. We also have people and robots trying to develop new mathematics out of it. And my vision, I was asked, I think 10 years, five years ago, about a prognosis where we would be in 30 years for some book to honor work on people. And I said in 30 years, we'll have the theory of everything physics figured out with the help of computer algorithms. I hope that's true. The other predictions I had for 10 years and 20 years all had to do with using virtual avatars to fake human relationships. So not so optimistic. The other example I gave is do something with quantum cryptography. And the third one, to be sure, I have only robots here because this is fine use application for the blockchain. And I think that's so hopeless. I don't want to waste human lifetime on that. My experience is that I became a blockchain expert by reading the Wikipedia article on blockchain and on Merkle tree. And ever since I've been asked to supervise that I see this industry of blockchains and always go in there and say, what's your untrusted party? And look at me with blank eyes, and then I know the project is lost from me. Okay. Yeah, this is my particular advertising slide. I think ATPs will be at the heart of the future AI math acquisition, but then I built ATPs, or one particular ATP, both for scientific gain and for fun. And so this must be my position. Also very nice, colorful. Okay, let's come to the end. So the one thing I normally state up front, but forgot this time, I think automated reasoning and machine learning. Reasoning and learning are the two pillars of intelligence. Automated reasoning and machine learning are the two pillars of artificial intelligence. These complement each other in various ways, and I think we need to use both. We have both if we ever want to have much better systems than we have now. I also think, at least in the field of mathematics and computer science, our core systems need to be symbolic and use sub-symbolic and symbolic methods surrounding it to help support the logic systems. The big LLM hype will, I think, collapse in the next 5 years or so. It doesn't mean that they're useless. You all know the Gartner hype cycle where it goes to the valley of despair and then comes up again to the plateau of usefulness. They are amazing, they're useful, they are fun, they can do many, many things. But I don't think they can do native mathematics. They can only help certain aspects of doing mathematics. And for my particular subfield, there's lots of other AI techniques that I use, and I think that are more helpful than LLMs in finding proofs automatically. Okay. Thank you. Yeah, any questions?
Wonderful, great future you have presented to us. So welcome, Schulz.
Thanks. Can you say a bit more about how you do the conjecture guided proof search?
Yeah, I don't.
Okay.
But I've heard the talks from farmers. So when I worked with Udo, the idea was really to enumerate consequences of our theory and then filter them for interestingness. The problem is nearly all of the consequences we have are boring. You all know we can say 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, 4 is equal to 4, and about 51, most people agree just become boring.
Yeah.
So another way is our students are a lot better when they have a direction, something they can, something we want them to try. Even if they don't, even if they can, they're still better. We found that out the hard way. Eventually, when we worked with this big series, and that was inspiration for this consistency checker. If you give psych to a theorem prover, it will just time out. But if you tell the theorem prover, use psych to prove this property, it will often say, oh, I found an inconsistent subset of the axioms. What Moore is doing, and I think MLCP is doing something similar. They have various tools, both symbolic and LLM based, that you can give examples of theorems, and then they will spit out conjectures. Some of them are based on patterns, so you have with these axioms appear, try the following 10 properties, maybe one of them, some of them hold. And that's of course it's very efficient, it's very cheap, but it's quite brittle. And so the new tool is they train LLMs on if these are the axioms, then these properties hold. Then again they ask them, here's a set of axioms, tell us some possible conjectures that might be. And then you try to prove them, of course. If you succeed, you have the theory. If you fail, you're still in the dark, know if it's true or not.
Welcome.
Yeah, so thank you. These great perspectives. You mentioned again this, and you also said that we have a kind of ongoing discussion about this, using LLM for translating. And I think if you say translating, if you take the last slide still, I think
This
go back to your last slide, because I think it has the conclusion slide.
Okay.
Yeah. So yes. So if you think about this very task of translating between different formalisms, so that's, I think that's typically a mathematical problem. So you are translating between three structures, and then you have to obey some semantics. And this is the thing that LLMs, as you said, are not very promising to do.
Yes.
And therefore, I think I would propagate symbolic solutions for that. And for similar reasons, I think natural language in this kind of precision, level of precision should be seen as three structures, and which have their semantics. And therefore, LLMs can help, and I will try to say something about that in the next talk. But I think the symbolic component should be
I've got
not even there.
but I have thought about that.
Yes.
So one thing is there are symbolisms that are just hellowly different. So the difference is like between C and Pascal.
Yes.
In programming languages, or between GPTP syntax and SMT syntax.
Yes.
So they restricted to whatever, where they have an intersection. And there I think LLMs can work quite well. Because you don't have to do a logical explanation, just have to do a syntactic explanation. Of course, you can do that automatically as well. So I get your point, but I think that's something they can do with a little bit of training. The other thought has vanished. Natural language as trees. I'm not so sure. I'm not a linguist, but one thing I've experienced myself is that at least when I speak, I don't speak in a proper grammar. I try to write a proper grammar, and then you can pass it to a pass me, of course. But human language is incredibly flexible, incredibly hard to completely capture in some form of grammar. So if you have a control natural language like in approach, or maybe in what is the lingual system, then I can see that this might work. And formal language in scientific texts often is much more controlled than when we speak among each other. Young students talk to each other, but I don't know what currently they talk about. Probably some kind of music or some kind of thing on Instagram. Yeah, I can see it's easy to translate from or the argument completely holds for translating from logic to natural language. But I'm not so sure what's the other direction, because human language is fuzzy and ambiguous, and that's something that LLMs can capture. Of course, then you need to verify that they actually translate it correctly. And that's again something where formal logic systems can help you by checking for consistency, by checking that you actually things that you believe are true, and things you believe are false. So you can probe them, the translation, and see that you get the effective results. Okay.
So no questions and comments. Please welcome.
Yes.
Okay, welcome.
So the papers that you mentioned, which are on why LLMs hallucinate and why what's happening behind them if we are doing mathematical reasoning. Do you have any do you know the reasons? If you can summarize them a bit or tell a bit more about their arguments.
I've got two papers here on hallucinations. This one is very new, and I only looked at it. I got it 4 days ago, so again, while I was here. But my understanding is that they make the argument systems are probabilistic, and by training them, they get rewarded for successes. That is, if they say nothing, they get no reward. If they guess, they get a reward. So they have a chance of getting a reward. So their solution is punishing them if they guess wrong, encouraging them to say we don't know if they don't know. I don't know if that's feasible because it doesn't quite fit the architecture of LLMs, but that's what they propose. The other paper, LLMs will always hallucinate. I understand it, and I don't understand it very well. They make an argument that you can embed undecidable problems into LLMs and force them to answer them, then they must hallucinate. And because this undecidable problem is part of the world, they also need to hallucinate of the real world.
I would like to make a very brief comment. I think what we all need to realize is that it's not surprising that LLMs hallucinate. Every word they generate is hallucinated. The interesting thing is not that they sometimes hallucinate, but that they almost always hallucinate things that make sense. And once we realize that, much of the mystery goes away.
Yeah.
Because that's what they're
And I mean,
built for
I've,
hallucination, good hallucination.
I've criticized them a lot, but one thing I also noticed is many of the failure modes of LLMs are also failure modes of humans.
Absolutely, yes.
So we are not perfect either. Well, nobody claims that, I hope. Maybe what was that Voltaire said, we live in the best of all possible worlds. And yes, it can as human intelligence, it must have certain failure modes.
Continuing on the topic of hallucination, so LLMs are basically random sentence generators with some biased probability.
Bias learned from
Yes.
yes.
And then when they encounter a situation which they are not familiar with, then of course they will just generate something random. And this actually happens quite often. So I have seen that if you just ask the model to generate something without giving enough, maybe only one or two words of context, they start generating garbage basically because they are in an unfamiliar situation in that case.
In the early days, they now built in safeguard, but you could just give it random voice strings, like blah, 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 blah. They would start using literal sequences of text they had read because they had basically no useful context. So they started somewhere and then suddenly they had context that they've seen before and would just string along this thin line of evidence that's completely random. And then it forces them to produce a sequence of tokens that they have seen before, essentially, because it's frequent in the input. Yeah.
Some more questions and comments and suggestions or refutations.
From a time point, you also 12 o'clock perfectly.
Yes, just a quick question which is related to what Arne said. So when we translate between formal systems, specification or programming for specific provers or verifiers, so then my question is, what do we do with the huge library? Mizar is one of the original system proof system, and the core of Mizar is a wonderful formal language. It's mimicking natural language in a perfect way. It used to be so nice when the library was small. Now the library grew tremendous, and I myself am giving up as a human to spend weeks or days to figure out what has been proved and what I have to try to prove, etc. And how it's so. What do we do with this problem when we translate between systems? Different provers, they have different libraries. And how do we handle that? Because those will be epistemic in hallucination, my hallucinations. I'll consider this the library as a system of epistemic states, and we need to select, you enumerate them, and we need to select only the useful things, not just the whole library.
One problem I see is that every translation loses something. And if you translate from one logic to another logic, you lose structure. You need always lose structure. And then translate it to a third logic. Then for proof checking, you want to translate maybe everything down to lambda pi and use deductive. But I think if you, that's like if you compile a C program into assembly language, it's very good for executing it. But you really don't want to upcompile it to Java. Take it as an example of a Java program. So going down, going towards more primitive languages is relatively easy. But if you then want to go up again, there's no easy way to recover the structure that you had at one time. It's a problem. I don't know an easy way to solve it. Of course, you can try to translate directly between languages, but then if you have n languages, you have n-1 squared translators, which also may not be particularly manageable.
So it's an open task.
one thing I learned as a scientist, and I don't know if it's exhilarating or depressing, but the more I understand, the more open questions I see. So I feel stupider and stupider all the time. That's the only thing that grounds me is when I talk to first-year students, and I notice how much back I have to go to be able to have a common language with them. How much I've learned in my 35 years as a scientist, but it doesn't feel like a lot. It's like, all natural numbers are small by definition, because for everyone there's only finitely ones that are smaller, infinitely many that are bigger. So relatively they're small. And I've got the same feeling. What I know is very little, because I always see beyond the border everything I don't understand, and that's always getting bigger and bigger and bigger. But yeah,
Okay.
I think that's our life. Sorry, my life.
So thank you very much again. Page 19 is probably, we have to put it on the website and for the future, for the next mathematical and computational linguistics. So now we have time. Probably the same electron.
That's the expert. Nice. Okay.
So to remind you,